In this question, it is given that let the function f takes r to r and g takes r to r be defined as fx equal to this thing, gx equal to this thing. Then the number of points in R where f naught g is not differentiable is equal to, you have to find the correct choice. Note that the values of x at which f naught gx may be non-differentiable. Note that I'm saying may be non-differentiable are those values of x at which g is non-differentiable, or those values of x when gx takes those values for which f is non-differentiable. What I mean to say, when I will do the question, you will understand it more clearly. First, let us discuss about the differentiability of gx. It's clear that for x less than 1, it is a polynomial, hence always continuous, always differentiable. For x greater than 1, again a polynomial, hence always continuous, always differentiable. And at 1, it is clearly continuous, but non-differentiability, if it is there, then it can be only possible at 1 only. Therefore, to check the differentiability at 1, I'll be using the shortcut way of finding the differentiability at 1. Shortcut way you must be knowing, and if you don't know, then you must see my video lecture of differentiability of JEE level. Presently, the left hand derivative of gx at x equal to 1, that is g dash 1 minus, is equal to limit x tends to 1 minus, and here you will be writing the derivative of this, that is 3x square. Answer is 3. And g dash 1 plus is equal to limit x tends to 1 plus, and derivative of this is 3, that is 3. Hence I can say gx is differentiable at 1 also. Hence gx is always continuous, always differentiable. And to proceed further, first I will find the value of x where fx is non-differentiable. Clearly at x equal to 0, fx is discontinuous. Hence at 0, fx is non-differentiable. But actually we have to discuss about the differentiability of f naught gx, that is f of gx. And because fx is non-differentiable at 0, therefore f naught gx can be non-differentiable only at those points where gx becomes 0. Note that I'm saying this can be non-differentiable at those values of x where gx becomes 0. And now let us find the value of x for which gx be 0. If I put this equal to 0, I will get x equal to 0. Note that this part can never be 0 for x greater than equal to 1. Hence, gx can be 0 only when x is 0. Hence, the chances of non-differentiability of f naught gx is at x equal to 0 only. To find the right hand derivative of f naught gx at x equal to 0, first let us find the value of f naught gx where x is slightly greater than 0. When x is slightly greater than 0, the value of gx will be given by x cube. Hence we get f of x cube. Note that I'm saying x is slightly greater than 0. Hence x cube will be slightly greater than 0. And keeping this definition of fx in mind, I will get this is equal to x cube square, that is I get x to the power 6. Hence I can say the value of f naught gx is x to the power 6 for x having the value slightly greater than 0. And therefore, if I name it as hx, then h dash 0 plus will mean limit x tends to 0 plus derivative of this, that is 6x power 5, that is 0. To find the right hand derivative of f naught gx at x equal to 0, first I will find the value of f naught gx in terms of x, where x is slightly greater than 0. Hence, this will become f of gx. This is equal to, if x is slightly greater than 0, then I will be using this definition of gx, that is, I will be getting f x cube, and this is equal to, now because I have supposed x is slightly greater than 0, therefore x cube is also slightly greater than 0. And using this definition of fx, I get x cube square, that is x power 6. And if I name it as hx, it means the value of hx is x to the power 6 when x is slightly greater than 0. And now again find the value of f naught gx, supposing x is slightly less than 0. In that case, I will get hx is equal to f naught gx equal to f gx equal to, when x is slightly less than 0, still I will be using this definition of gx, that is x cube. Hence I will be getting f of x cube, and because x is slightly less than 0, therefore x cube is also slightly less than 0. And using this definition of fx, I get x cube plus 2. Hence the value of hx is this thing when x is slightly greater than 0. The value of hx is this thing when x is slightly less than 0. And for x equal to 0, the value of gx is 0, and the value of h0 is equal to f of g0. This is equal to, clearly g0 is 0, that is I get f0, and f0 is 0 from here, 0. Hence I can easily say that the function is discontinuous at x equal to 0, because value of function and right hand limit will be 0, but left hand limit at x equal to 0 will be 2. Hence hx is discontinuous at x equal to 0. Therefore hx is non-differentiable at x equal to 0. That is, f naught gx is non-differentiable at x equal to 0. Hence the number of points in R where f naught gx is not differentiable is 1. That is, D becomes the correct choice.